So in the last class, we have discussed about sintering process, and we have seen how the heat front and the flame front are moving along the thickness of the bed. And today we will discuss about a concept called matching. So this is very important. As I said that whenever the heat front and the flame front, when these two matches, then at that particular area, the bed will reach the maximum temperature. Wherever the center bed reaches the maximum temperature, there the sintering will take place effectively. So if you see in this particular picture that this curve shows that this is one layer. There are a series of layers of there. This is one layer, this is another layer, third layer, fourth layer, like that. And these also layers. So this is the x-axis, this is the y-axis, you have the temperature, and x-axis you have time. So as the bed is moving, so this layer, first layer you can say, this layer has attained the maximum temperature, that is around 1350, something like that. So this is only possible when the heat front and the flame front are matching. And ideally, the bed, the temperatures of all the layers that are present in the bed should have ideally like this. The dotted line shows the ideal condition. So if this follows, then all the layers of the center bed are undergoing proper sintering. And this will happen only the flame front and the heat front matches together. If not, if suppose the flame front and the heat front are not matching, that mismatching is taking place between the flame front and heat front, then at that layers, center bed cannot attain the required maximum temperature or required maximum sintering temperature. In that case, the mismatch may take place. So you can see only the first layer is attaining maximum temperature, and the rest of the layers you can see layer 2 is also okay to certain extent, but you can see from layer 3, layer 4, layer 5, all these are having temperatures less than 1000 degrees centigrade. It means only if first layer is perfectly sintering, second layer is okay to certain extent, it is having proper sintering, but from third layer onwards there is no sintering taking place. There is no proper sintering taking place because the layer is not attaining the maximum temperature. It is due to because of mismatching of heat front and the flame front. So then the kind of sinters what you produce in this case will have poor sinter properties. So and the productivity of this sinter bed will get hampered. So if when the sintering is not taking place properly, then this sinter mix will be again recycled or reused as sinter returns. So when you can see in that particular picture that above 1000 degrees centigrade, layers where you have temperatures more than 1000 degrees centigrade, So what is happening here and what is happening in the other layers is the layers which are attaining temperatures above 1000 degrees centigrade will have good fusion and good bonding may takes place between the particles and sintering takes place effectively. Whereas the layers which are attaining a temperature less than 1000 degrees centigrade, where the localized fusion is not taking place and the bonding between the iron particles are not taking place, which leads to fourth center. At the end of this strand, once the flame front has to reach to the utmost part, that we call it as a burn through point. So the flame, as the bed is moving, flame front moves from top to the bottom, and once the bed is reached towards the end of the center bed, the flame front has to reach to the bottommost part. Otherwise, the bottom part will not get sinter. The bottom layers will not get sinter. There are two terminologies. One is the flame front that represents the combustion zone. Another one is the burn through point. It represents that the combustion zone has reached to the lowest layers of the bed, almost near to the grade bars. So when the combustion zone reaches to the grade bars, that represents the completion of the sintering process, where we can also call it as it is a burn through point. So when the flame front approaches to the bottom of the sinter bed, as I told you that there are wind boxes which are present below the bed. So for every wind box there is a thermocouple is fixed, and once the combustion zone or the flame front reaches to the bottommost part of the bed, then there is a significant increase in the temperatures in the wind boxes. So that will give an idea that the sintering is taken place completely. So by the time the combustion zone reaches the lowermost region of the bed, the iron ore particles will get agglomerated owing to the partial melting at the surface, and there is a slag formation is also taking place completely. So because of this slag formation, so slags are basically the slag whatever it is formed because of the incipient fusion of iron ore particles. That slag is basically act as a bond between the iron particles. So there are iron particles and these all iron particles are bonded together with a slag bond. That is actually what happening in the sintering process. And this burn through point usually we attain this condition, that is the sinter bed is the sinter bed the lowest layer of sinter bed attains the maximum temperature. That is called burn through point. This we basically attain at least 2 to 3 blocks ahead of the end of the sinter stand, because before the sinter comes at the end of the stand crushing, it should become cold by forced air cooling. So if suppose BTP is not achieved at the end of the strand, means there are certain amount of unsintered raw mix is present, and this unsintered raw mix will be again used as a sinter returns. Also, you can see the time taken from the bed to move from ignition hood to the end of the sinter bed. So that is called as we do it as a sintering time, and this will be approximately around 30 to 60 minutes. So the sinter, whatever it is produced, that will be crushed and screened before we charge into the blast furnace. For this purpose, the sinter cake from the machine is cooled down, and then that cooling will be done on the annular cooling system. and then broken into suitable sizes. Generally, for blast furnace, we maintain a size of around 5 to 40 mm. That is a reasonable size for the center size for the blast furnace. And minus 5 mm, whatever are there. So this minus 5 mm, we call it as sinter returns, that will be used in the form of a earth layer on the sinter bed. Around 50 mm earth layer we basically add it. So after crushing, the final cooling of the sinter before it is proceed further is carried out in a separate sinter cooler by air and air cooling area. I told you that this cooling of the sinter basically takes place on an annular moving bed, sinter bed, and the suction basically takes place from the top. So we basically do the cooling from the top suction, and that heat, whatever we have recovered while cooling the sinter, that is used as in the handling hood, which is arranged in the front of the ignition hood. So the temperature of the sinter after cooling will be around less than 100 degrees centigrade, and screened underside sinters are recycled, and oversize will be, that is around 5 to 40 mm size, whatever it is that will be subjected to for blast furnace charging. So this is what it is what all about the sintering process. But what is actually happening on the sinter bed during sintering process? How the raw mix behaves and what is happening? You see, we are adding. Let us say we are adding the hematite ore, the Fe2O3, and when this intermix means, which you can see of iron ore particles, then you have a fuel, then you have fluxes. So this entire mixture is actually subjected for the combustion process. The top layer of the sinter bed will undergo combustion when it is subjected for the ignition hood. So there, once the top layer get ignited, then the fluxes, whatever it is present, that will get that is CaCO3 get dissociates, Ca1, CO2. So that CaO will react with your iron bearing material and forms a low temperature, there is calcium trite. So this is a low temperature phase. So because of which the fusion of the iron bearing particles takes place at around 1200 degrees centigrade, and then because of the localized diffusion of iron bearing material, gangue content, whatever is present in iron bearing material, will basically comes out, and that is consist of Al2O3 and SiO2, and this Al2O3 and SiO2 combined with CaO and form a slack phase. So this slack phase will bond the iron bearing particles. So this entire compound is nothing but 2 Fe2O3, CaO, Al2O3, SiO2. This is silicate of calcium and aluminate. Where you can see this is Fe2O3 is iron bearing material, and rest CaO, Al2O3, SiO2 is the slack phase. So schematically, if you see, this is how the sintering basically takes place. That is the bonding of iron bearing material with the slag. Slag is the slag bond, and the iron bearing materials are agglomerated. And the sinter mineralogy. So during sintering process, how the phase transformations basically taking place with respect to the the amount of fluxes what we are added during sintering. If you see, this is very important because one can correlate various types of bondings and the quality of the sinter, the evolving mineralogy of the sinter. In this picture, if you see, suppose if there is no flux is added to the sinter mix, that means you can say the basicity CO by SO2 ratio is less than 1, much less than 1, or almost it is equal to 0 either. Then in that case, see the kind of the bond which are formed is all of around silicate bonds, where you can see here this is silicate bond, and formation of these silicate bonds basically requires a very high temperature. That means it requires a very higher fuel rate. But the problem is that high fuel rate because of high fuel rates, the Fe2O3, the hematite ore, may get partially reduced to magnetite or oostite. And the presence of these silicate bonds, silicates basically form strong bond, but they have very less reducibility because of less hematite. And if you add little bit amount of fluxes, suppose around if the basicity is around 0.5, then you may see a certain amount of glassy phase which is evolving. And this glassy phase is of around CaO, SiO2, FeO, that fuse at much lower temperatures, which reduces the fuel rate and attains the hematite phase in the sinter and make it more reducible. But the strength of the sinter may get reduced. Even though the reducibility increases, but the sinter strength may get reduced. Still, if you increase further the fluxes, that is CaO content, if the CaO by SiO2 ratio reaches to around 1.2, in this case, the precipitation of ferrites and silicates may take place. That means the amount of glassy phase still increases, fuel rate decreases, and sinter strength will be becoming much more less. Still, if you increase the basicity from 1.2 to around 1.4 to 1.6, where there is a possibility of dicalcium silicates formation may take place, which may weaken the sinter. But if you add CaO by SiO2 around 1.6 or beyond that, you can clearly see there is another phase which is forming, there is calcium ferrite phase, which is evolving beyond CaO by SiO2 of around 1.6 and above. And this phase, calcium ferrite, which are needle-like structures that holds the sinter particles tightly and thereby increases strength. The advantage of this calcium ferrite phase is it demands less fuel rate, and also it is more reducible. Above that, it retains the hematite phase. So this is the advantage of having a Sinter mix with density more than 1.6. So based upon the amount of fluxes which are present inside the Sinter, the Sinters are classified into two classes. One is non-fluxed Sinters, other one is the fluxed Sinters. Non-fluxed Sinters we can also call it as acid Sinters, where there is no flux is present in the ore or may not be added during the sinter making process. And flux sinters where flux has been added or to a certain extent is present in the ore. And these flux sinters are again further classified into two types. One is the self-flux sinters, and another one is the superflux sinters. Self-flux sinters means where the density is greater than 1, where sufficient flux has been added in the sinter mix, provide a density that is desirable in the final slag, taking into consideration of the acidic oxides which are present only inside the starch mix. And apart from the flux which is going in the form of sinter in the blast furnace, an additional amount of fluxes will be added to cater the needs of or to cater the or to take care of the SiO2 which is generating in front of the TS during the combustion of the coke. Whereas in the superflux sinters, having the basicity greater than 2, that means we are adding fluxes to the sinter during its manufacturing by considering the acidic oxides which are joining the blast furnace from both iron bearing material as well as the coke ash. By considering quantity of SiO2 which is joining from these two, fairly itself we add the fluxes during the manufacturing of the sinter. So those are called as superflux sinters. Certainly, generally they will be having the density greater than 2. Next one is the sinter productivity. For any process, the productivity of the particular machine or furnace, anything, is most important. There are various factors which contribute to the productivity of the process. Similarly, here also in the sintering process, there are various factors which contribute to the productivity of the sinter machine, like raw materials, quality of the raw material, the charge preparation, what we are doing before we subject the mix onto sinter stand, the geometry of the sinter bed. The most important thing is the flow of gases along the thickness of the bed. So there is a formula which represents the productivity of the sinter bed. It is 60 into P into H into P into minus RF into Y, where B is the productivity of the sinter, B is the bed depth, excluding the earth layer, H is the width of the stand, and V is the speed of the horizontal movement of the stand, Rho is the density of the mix, RF is the amount of sinter returns, and Y is the yield of the sinter. So when we say the sinter is having good quality, when the sinter is having high room temperature strength and low reduction degradation index and high reducibility. When the sinter is having these properties, then we can call it as a right quality sinter, which can be preferable to charge as a feed material inside the blast furnace. What are the factors which is affecting the sinter quality? If you see, first one is the particle size. Uh, we basically maintain certain size range for all the raw materials which we are using in the sinter making process. Because finer the particles, more is the surface area, and there is a more possibility of interaction of gas and the solid may take place effectively to which the sinter productivity or sintering process will take place effectively. So particle size is very, very important. In general, you see the mix instead of coke is of 4 to 5 mm size, fluxes of around 7 to 10 mm size, and so we maintain proper size ranges so that we can attain proper contact, surface contact between the gas and the solid. The solid gas interactions will take place effectively if you have a larger surface area. And the moisture, so the amount of moisture which is present in the sinter bed is also very important, because if the moisture content is very high, then the heat requirements will be more. So then the fuel rates will be increased. And there is a possibility that sintering cannot take place effectively because of proper phase formations may not take place. So an optimum amount of moisture should be added so that the every layer of the bed will attain the uh, maximum temperature. There is a matching of heat front and flame front should take place effectively. So the level of the moisture in the sinter bed is around approximately 3.5% to maintain. Again, fuel also. The amount of fuel rates, the fuel consumption, the fuel rates is also very important. Large amount of fuel consumption may also lead to phase transformations. Then the reducibility of the sinter may affect. So an optimum amount of fuel consumption should be maintained. So generally, large amount of fuels in the sinter mix increases sintering rate by giving high flame front speed if the airflow can be increased. But the maximum temperature increases with more fuel. So this will certainly influence the nature and extent of the slagging, and of course the sinter quality also. Other thing is the fluxes. Just now we have seen the amount of fluxes what we need to add. So that will decide its mineralogy, and certainly production rates be increased if you add an optimum quantity of fluxes in the sinter. Next one is the advantages of using sinter in the blast furnace as a feed material. Any free or combined moisture in the ore is removed and the carbonates are decomposed. So if you are using sinter as a feed material inside the blast furnace, then certainly the fuel rates will be reduced. A part of the sulfur present in the charge is removed during sintering process. So the amount of sulfur joining into the blast furnace can be reduced if you use sinters as iron bearing material inside the blast furnace. The gang constituents of the ore are pre-slagged in the flux sinters. So it is already pre-slagged iron bearing material. So again, here also um, we no need of great amount of fuel rate for the uh, fusioning of iron bearing material. The amount of heat in the blast furnace is saved as dissociation of carbonates takes place. Yeah. So the endothermic reactions, whatever are there, which demands an enormous amount of heat if it happens inside the blast furnace. Those all endothermic reactions, the carbonate dissociations like that, that is especially the limestone dissociation and all, which demands an enormous amount of heat. So that once it has happened outside the blast furnace, then certainly you can save uh, the amount of heat in terms of amount of fuel also. So using superflux sinters, amount of limestone charge in the blast furnace is reduced, and thus the solution loss reaction is decreased. So this is also one of the greatest advantage of using sinters in the blast furnace. So we can reduce the solution loss reaction. So there will be carbon loss can be reduced. The evolution of CO2 gas in blast furnace due to dissociation of carbonates is much reduced. Therefore, this will favor the indirect reduction of iron ore. Productivity increases as the volume of material charged per ton of hot metal is reduced by use of superflux sinters. Yeah, because when you are already charging superflux sinters, then one of the raw material can be reduced. That is your fluxes. The flux consumption rate will be certainly reduced. So, when you see the volume of the raw material what you are charging, certainly that will be reduced, and there is a more possibility of adding much more iron bearing material inside the blast furnace. That will certainly improve. The irregular shapes of sinters help to maintain adequate permeability and permits high blowing rates. Yeah, and moreover, if you see the morphology of this sinters, they are having very good porosity. So the diffusion of reducing gases within the sinter is very much effective, and the reduction rates inside the blast furnace also will be more. And you can see the sinter chemistry. That is the FeO 9 to 10%, CaO 12 to 13%, SiO2 5.5 to 6%, MgO 1.9 maximum, Al2 to 3.5 maximum, HCT 2.2, and rest is yeah. So this is how the sinter looks like, and this is the rough chemistry of the sinter. So with this, we have finished the sinter part. The next class we'll discuss about the pelletization process. Thank you all.